Okay, kiddos, it's now time to put our analysis theory into practice with an example. And I want you to look specifically at the problem of summing a list of numbers. And we'll do it in two parts. In this first part, let's ignore the possibility of floating point rounding errors in order to build your intuition for what a correctness analysis looks like. Now let's start by formalizing the problem. Let x be a collection of n input values numbered from 0 to n minus 1. The function you want to compute, f of x, is the sum of all these elements. Now here's an algorithm to compute the sum, implemented as a Python function named algsum. Its argument x is the collection of input values. Let's assume this collection is iterable, meaning you can loop over its elements. Now the algorithm uses a temporary scalar variable s to hold a running sum. It initializes that s to 0 in the first line. Now notice that the initializer is declared to be a floating point value, so let's assume that we might expect the input x to also contain floating point values. Now in the body of the for loop, it accumulates each element, and then it ends by returning this value s. Now I know what you're thinking. Isn't it obvious that this program is correct? Well, maybe, but I want you to wear your computer science hat for a moment and ask yourself, how would I prove that it's correct? After all, the code involves floating point arithmetic, which is approximate, so how can you be sure? Let's start by ignoring floating point. That is, let's do an analysis in exact arithmetic, assuming no rounding errors. Now consider this temporary variable s, which is the object that keeps changing and eventually holds the output. Let's start with an assumption about this loop. In particular, suppose it produces the elements of x in order, meaning x0, then x1, then x2, and so on. Next, let s hat sub I denote the value of the variable s at the end of each loop iteration. That is, s hat sub I is the value of s immediately after the update to s occurs inside the for loop. For example, s hat sub 0 will be the result of the first addition. Now from this notation, it would also be natural to define s hat sub -1 to be the initial value of s, which is 0. Lastly, to understand the result of this function, let's assume that the input values are exactly the same as the collection of the xi values in the problem statement. If instead the input has errors of some kind, you'll just need to propagate that error to the result somehow. But let's worry about that later. So here's what you want to know. Returning to the end of the loop body, what is the value of s hat sub I? Well, it starts with the value just before the update, s hat I minus 1. Then it accumulates the next value from the collection, which is xi. Now you can ask again, what is s hat I minus 1? Well, it's a similar thing. It's the previous value, s hat I minus 2, plus xi minus 1. And you can keep going like this, expanding the recurrence. Now going all the way to the beginning, you'll end at s hat minus 1. And that's the value which is just 0, since it's the initial value before the loop even started. So s hat sub I is just the partial sum of all the elements up to xi. And that's all well and good, but the value you want is the return value. But that's just s hat sub n minus 1. So that must be the sum through xn minus 1. And that's exactly what you wanted in the first place. Of course, this analysis assumes exact arithmetic, but the whole point of the module is that finite precision means there'll be rounding errors. So now's a good time for you to pause and review what you just did. When you come back, we'll discuss how to reason about correctness in the presence of rounding errors.